So I'm here to talk to you guys about benchmarks and what they are and why is it interesting and kind of useful to have them or to like sort of start writing them, I guess. So a little bit about me. I'm Alex Navasardyan, too cool on GitHub, too cool on Twitter. I work for a company called Dockyard. We're Ember.js, Rails, mobile consultancy based in Boston. So benchmark is hard, especially when we talk about benchmarking your JavaScript code. And that's because we are working with browsers, and browsers are they're actually sophisticated pieces of software. Because when you run your code, JavaScript code, it gets executed. It actually executes native code, which is an assembler, right? And then JavaScript engines, they are written in C++. And then, there's a complexity of your JavaScript code, because your JavaScript code can be really sophisticated depending on the framework that you're using, like Ember.js or Backbone or whatever, right? And another quirk of benchmarking is hardware. Hardware is a big problem, because, not actually a problem, but you sort of have to be aware of that. If you want to know or reliably run benchmarks and have reliable results, you're better off having a server, a standalone server that does nothing but just runs benchmarks. So that is kind of hard. It's like a lot of moving parts, and why even bother, right? So given that we're all writing JavaScript and we're all web developers, we should be aware of that. When you run your code in the browser, you're only just scratching the surface. So you're only touching this one layer, which is JavaScript, right? So again, your code, then there is a compiler. And what do I mean by compiler? Compiler is actually not the, I would say, proper term for that. It's more like JavaScript engine. Compiler is a part of the JavaScript engine. So Firefox has SpiderMonkey, Opera has Karakan, IE has Chakra. But I'm going to be specifically talking about V8 here. So your code, JavaScript, is being run by the compiler. So compiler does something to it, and then it turns on the native code. So it turns out that the code that you write, your JavaScript code, is actually not the same code that gets executed. Sounds kind of bizarre, right? So what is going on? Right. So for that, I'll talk a little bit about compilers. It's just sort of a compilers 101 thing. This example is called constant propagation, right? So what we're trying to benchmark here, we're trying to benchmark converting a string to a number. And there's double tilde operator. If you guys didn't know, that's just an equivalent of parseInt. So we have this constant, a, right? And we're running 1,000 times a loop, and then we measured the time. We just log it on the console, right? So it's kind of simple, right? So this is the code that we're working with. But compiler is kind of smart. So what it does, it looks at the a and says, well, it's a constant, right? So I might as well just inline it like that. Cool. Then it looks further and it goes, well, it's a constant, and all you do, you're just basically converting a constant. So I might as well just perform this operation once. I'm just going to convert it once, and it's just going to inline it again. And at this point, you're benchmarking the assignment. Cool. All right. So let's take a look at another example. So a smart developer will look at that and says, you know what? Let's make a non-constant. Let me use date.now to string. So not using constant anymore. Awesome, right? But compiler will take a look at that and say, well, you know what? It's all good. But I'm just going to hoist out that operation, that conversion, out of the loop. I don't have to do it many times, right? So I'm just going to create a new variable, and you are benchmarking the assignment again. So it's totally not what you think is going on. And even that is called loop invariant code motion, when things are hoisted out of the loop. So it's all good. And then compiler looks at the code and it goes like, okay, so nobody's using C, that variable over there. Nobody's using B. So why the heck am I doing all this crazy work? Pfft. Gone, right? And now your code is infinitely fast, which is awesome, right? Your benchmarking are like gets you like really nice results. You high five your colleagues, right? And you call it a day. Nice. All right. So given that, oh, there's another thing called inlining. So if you ever want to benchmark your function, and I took this one as an example. So you run this code, right? So it basically takes 4 arguments and it just puts them together, right? So what compiler will do, it'll actually look at the function and say, I might as well just inline it, right? And it does this, and at this point, you are putting a string together, which is a constant, which is going to be eliminated as well. So you benchmarking nothing. All right. So given all that, given all this complexity and like weird things that are happening under the hood of the JavaScript engine, like why even write benchmarks, right? Why do I bother? Well, the first thing, it actually helps you understand what is actually happening to your code, how JavaScript engine works, right? So, and given that you understand what's happening, you can improve your code. You can help the compiler to run your code faster, which is, generally good. The code runs faster. And after that, you can measure and validate all the assumptions that you made. That means that you can have a suite of benchmarks that will run over time. And, well, first off, it's going to tell you, like, it's X% faster or it's X% slower. And the more important is that it will allow you to validate the assumption that you took. So let's say V8 optimizes the code very well, so your code runs faster. But SpiderMonkey doesn't. It's just, like, it's actually slower. So you will be able to find the balance, which is pretty awesome as well. So given that, it seems like you have to know a lot about, like, you have to know a lot of things to write benchmarks. But that's not actually true. You just have to know a little bit about compilers. And you don't have to know how compilers are implemented, nothing crazy like that. You just have to know basic things of like how compiler operates, how compiler thinks about the code. So this particular feature, hidden classes, this is something that is implemented in V8, and this is how V8 optimizes the code. So it might sound complicated, hidden classes, but hidden classes are just metadata. So anytime you create an object, it creates a hidden class. So why do that, right? Well, the problem is that JavaScript is a dynamically typed prototype-based language. That means at any point of runtime, you can take the object, you can change its type. That makes it really hard to optimize the code because you don't know the type. So like, what do I do? What is going on? So that's why V8 creates all the hidden classes. So he stores the type information, and this type information allows him to optimize the code. So this particular example, we have a function called person, and we create 2 instances of the function. The Iron Man and the Captain America. So let's see what's happening here. So we are executing function new person. So as soon as we, inside the body, it creates the hidden class CO. It's actually not the real name, I just made it up, CO, whatever. And as soon as we start adding new properties, it's going to create new classes. So now there's another class, C1, that based on CO with a perpetual first name. The same thing happens with last name. So now what you end up having, you have a chain. So now you know that the object that you get back from the person function has this chain and has this type. Cool. So what happens here, the next time we call new person, it's going to have the same the same chain, the same C2. So the classes, they match. And this is how V8 knows that I can actually optimize the calls and different operations on those two objects, Iron Man and Captain America. But as soon as you change the layout, or they call it a shape of the object, and changing the layout means, for example, assigning a new property that wasn't known to V8 before. As soon as you do that, it's going to create a new hidden class, which is going to be based on C2 with a new property called age. And this is bad. This is bad because the optimized code that V8 had before, it has to throw it away. Put the optimized code one and let it run. And then it's going to come up with new assumptions, et cetera, et cetera. All right. So given this feature, the hidden classes feature, that allows you to implement another feature, inline caching, which is huge too. It pretty much speeds up your code like 20 times. So what is inline cache? Well, obviously it is a cache. But what it does, what V8 does, it looks at the code, looks at the function, and actually not the function, pretty much everything. Let's say you access something very often, and V8 noticed that, and instead of like calling retrieve operations all the time, is going to just swap it with a fast path. So I'm just going to give you an example. So let's say you have these .puppies, and that's an array, and let's say this .puppies is hot. By hot, I mean it's used everywhere, many, many times. So instead of doing, and this is assembler code that gets generated by V8, so don't get scared, this is not relevant. All that's relevant is this, right? So the first time this .puppies is going to be accessed, this guy is going to be called. So it's going to call this function and go retrieve the value, either from memory or probably from memory, and it's going to get it back to you, right? But as it runs, V8 looks at that and says, well, you know what? I might as well just swap the function call with the actual address in the memory. So no more function calls. It just gets you back the value right away. It's an optimistic assumption, but it is usually valid. All right. So having said all of that about JavaScript engines and about V8, let's move to benchmarking patterns. It's like, how do you actually benchmark your code? What are the ways, right? So the first one is fairly simple, right? You write your code. You have a number of iterations, right? And then you run your code 6 times, like in this particular case, 6 times. And that's pretty straightforward. The downside of that is that as browsers, they get faster, and you end up having this 0 millisecond results. So it's unusable. So you don't know how fast or slow your code is. Another way of doing that is not relying upon the number of iterations, but relying on the total time. So you say, my benchmarks are going to run for 10 seconds, and then I'm going to measure the number of operations happen during those 10 seconds. The drawback of that is that the results may vary because of the JavaScript garbage collection and different engine optimizations, and also, as I mentioned before about the hardware, it actually is very important not to have any background processes running when you're running benchmarks, because that's going to affect the results. So anyway, to get more or less reliable results when you're using this particular pattern, you have to run it many, many times to get the average. Whoa. All right. This one is called the loop unrolling. So let's say you want to run your benchmark, the test one, right, X number of times. So the approach here is that you're not going to have a loop. So the loop gets thrown away. The test function is going to be inlined like that, and you're going to basically end up having you're going to inline your function X times. So the problem with that is this is actually going to increase the memory usage and slow down the CPU. So that's why for like when I do benchmarking, I use Benchmark.js. So those guys, John David Dalton and Matthias, I can't remember his last name. Anyway, so those guys, they wrote the Benchmark.js library, and this library gives you reliable, precise timers, and better benchmarking patterns. So those guys just figured it out, so you don't have to worry about like which benchmark pattern to use to run benchmarks. Anyway, so they use sort of like the combination of patterns A and B and the function body extraction. So long story short, so this is setup. This is how you typically write your benchmarks using Benchmark.js. So you have a setup function, which a lot of people get it wrong, which gets executed only once before the test cycle. So you have that, and then you create a suite, and then you add basically a test that you want to run. So this is the code that you see. This is the code you're interacting with. But under the hood, it gets converted into this. Don't sweat the details. It doesn't matter. Basically, what Benchmark.js is trying to do is tries to guard you from the optimization that V8 does and other JavaScript engines. This is what matters. So you have the setup code over here, and then the while loop. And your test executes X number of times. So given all that, let's move to the demo, and I'll show you what I typically do to run benchmarks. All right. Can you see it okay? Seems fine? Cool. All right, so what we're looking at is the typical setup, I guess. There's a backburner, and for you who doesn't know what backburner is, it's a famous run loop, Ember.js run loop. It's a micro library to basically queue a lot of actions, put actions on the queue and execute them, like batch execute them, I guess. So that's a backburner over here. Benchmark.js and Lodash. That's Lodash is a requirement from Benchmark.js. Then we have an actual test here and the index.html here. So I have index.html because the way I do it, you can open the instance of Chrome. I use Chrome Canary browser with specific flags that'll tell you. It'll just dump a lot of information about what V8 does to your code. So that's why you have index.html, because it's going to be opening this code in the browser. So let's do that. So for the sake of time, I'm just going to copy that over here. So what's going to happen is that you're going to see that the code is running in Canary. So Canary was open, and all this output is basically the metadata of what is actually happening under the hood and what V8 does to your code. So bear with me. All right, so it seems like it's fine. Yeah, seems like it's fine. And now, look at that. We have a lot of different files here. So all this ASM and CFG files, those are files, metadata files that basically contain information about different de-optimizations and things like that. So just to show you what it looks like, don't get scared, it gets better. So it looks something like that, right? Like this is total crap. I mean, like, you can't work with that, right? Tells you nothing as a JavaScript engineer. So what do we do? There's a tool that one of the Google engineers wrote, and it's called Hydra. And guess what it does? It actually helps you. Parse this information. So let's try to open this to you guys here. Yeah. Okay. Cool. Right. So notice that you have this long list of things over here, and this is the function that, when you call defer, this is the sort of under the hood function that gets executed in Backburner, right? So again, so you look at that, which is like, all right, what I don't know, and you see deopt, right? Something like it's something really bad, I guess. It doesn't tell you anything, right? So for JavaScript engineers, what? Okay, cool. So for JavaScript engineers, he actually implemented this source view, right? So what is happening, this is the de-optimization that happens, right? So, and this is where it gets tricky. It's a tricky problem, I would say, and that's a known issue in VA. Basically, what it does, it thinks. Anyway, that doesn't. I don't want to dive into details. Basically, having that in place, you can understand what is happening under the hood of V8 and why the de-optimizations happen. So in this particular case, there's a notion of what do you call it? I forgot what the function is called. But basically, when V8 works with one assumption. So in this particular case, like this means that the assumption that V8 made before is invalidated now. So now it has to spend some time de-optimizing the code and returning to non-de-optimized slow code. It has some road to go, and it's not perfect, but it actually tells you can figure out with a little reading of what is happening, what does it mean, or ping somebody on the emailing list of VA. So, and say you figured out the problem, or or you already, or even better, you fixed the problem. So you kind of know that you fixed the problem, you improve the performance, right? So how do I make sure that how do I test that? How do I run it in the long run, right? Or how do I compare it to implementations? So there's one little library that I wrote. I'm still kind of poking around that. It's called Perform. So basically what it allows you to do, it allows you to have two different implementations and one benchmark. So let's say we have implementation called master, which is an implementation of your library. In this case, it's Backburner. And then you have different benchmarks, which is in this case defer once, which some of them I created. Okay, so they look sort of like that. So this is the ES6 modules syntax. You have a name, then you have the initialize function, which is going to give you this object over here, the BB one, which is a backburner. So having the initialize function, you can pass values to your actual test like this. And this is the actual test that you're running. So, all right. Okay, so basically what it allows you to do, this magical command. All right. Right. So it just took one of the benchmarks, which is the Q1, and it ran it with implementation of master. So if you want to know like if you want to start poking around with the code and like try to figure out what benchmarks, pitfalls, and etc., you can create a new implementation. So let's call it tweak, maybe. Come on, there you go. So it's going to be a copy, right? And the copy is that the copy that you're going to be changing in order to improve your code. So you have one canonical master implementation, and then you have this tweak one. So now what you're looking at is that actually it took the same benchmark and it ran it against two implementations. So it's actually an easy way to, well, first identify what the problem is using V8 and that our Hydra tool, and then making sure that when you change the code, it actually reflects the optimization. So, I guess that would be it. That would be it for demo, and that would be it for a talk. So thanks you guys for listening.